Our goal in the warm-up is to find the missing side lengths, and currently all we know is Pythagorean theorem. So we're going to do the Pythagorean theorem to find the missing side lengths, and then we're going to reduce decimals. First thing I know, if I look at this triangle, it is an isosceles right triangle, which, by the way, because it's isosceles, we know that these two angles are congruent, and actually they have to add up to 90, so that makes this a very special kind of triangle. It's a 45, 45, 90 triangle. That's what we're going to be focusing on today. So I might hint at an extra little pattern, and we'll see if you guys can find out the pattern before we even learn it. But what do we know? It's isosceles. So this side is 10 and this side is 10. And then I'm going to just do Pythagorean theorem, and I need to find the hypotenuse, the c value. So I know that c squared is equal to the sum of the other two sides squared, which is 100 plus 100, which is 200. And then my goal is to get c by itself, so I'm going to take the square root of both sides. And then I have to split this up. Now there's two ways to split this up. You can play the divide by 2 game and keep dividing it by 2, but a better way to do this is to split up 200 into 100 times the square root of 2. Square root of 100, I should say. And the reason why is we know what the square root of 100 is. The square root of 100 is 10, and then the square root of 2 is left over. All right? So, now there's a little pattern here you might notice. Don't write this part, but what if I changed this to 18? All right, so what if it was 18 and 18? Any guesses on what the hypotenuse is going to be? Well, let's think of this. I'm going to have 18 squared and 18 squared. And whatever that ends up being, I'm adding it together twice. So I'm going to be able to split it up. And it's really the square root of 18 squared, which is just going to give me 18 again. So maybe your hint or your thought was correct. If I change these to 18, notice what my answer is for the hypotenuse. That's just a little bit of a trick or a hint at the pattern we're going to be looking at today. I'm going to get rid of those because that wasn't the original problem. It was just 10. All right, the next problem. Same kind of work, but now I have the c value and I have one other leg. Doesn't matter, I'm going to call it a. And let's just kind of go through quickly. So c squared is equal to a squared plus b squared. And I got to cheat and use my calculator. 24 squared is 576. And then we're going to subtract 144 both sides. And I get 432 equals b squared. Then I have to get b by itself. So I'll take the square root of both sides. And then I have to find the largest perfect square that goes into this. Now, you could sit and try to play the divide by 2 games and keep going. Here's what I did. I tried 16 right away. And I'm not saying this is the best way. This is actually a longer way. I just want to show you that you don't always have to pick the largest perfect square. So if I pick 16, 16 times 27 gives me 432. And I know what the square root of 16 is. All right, square root of 16 is 4. But I'm not done, because what's left, that 27, actually can be broken down into 3 times 9, or the square root of 9 times the square root of 3, which means the square root of 9 is 3. So then I've got 4 times 3, which is 12 square roots of 3, which tells me, wait a minute, what the square root of something gave me 12. A better route, a better answer would be picking 144 times 3. That's the fastest way to reduce this. I didn't see it right away. because 144 is 12. So that just shows you that if you don't pick the largest perfect square, that's okay. You just have to look at what's left over and keep going. All right, so we get 12 square roots of 3. Now, this is a special triangle as well that we're going to be learning today. And there's no way you could know this, but this angle right here is 60, and this angle right here is 30. It's a 30, 60, 90 triangle, and it's a special kind of right triangle that has a pattern much like the 45, 45, 90 triangle did. Notice one of the quick patterns. Across from the 30 is the smallest side at 12. And look at the hypotenuse. It's 24. That's a pattern there. So if I changed this 12 to 17, let's say this side length was 17, well then this length would be double that at 34. And notice here, 12 square roots of 3, if this side length was 17, this one would be 17 square roots of 3. So that's just a quick little pattern. I wanted to show it to you now. Let's get rid of that because that's not part of the original problem. All right, so there's a warm-up. We're going to start off by doing something called rationalizing denominators. This is an extra little skill that we're going to need to simplify our answers today. So we're going to just start off and kind of say, okay, what if I have a problem that says n squared of 3 equals 18? My goal is to solve for n, and we have to do something special here called rationalizing the denominator. It's basically simplifying it and getting rid of a square root in the bottom. So I'll give you a second to write this down. And our goal here is to get n by itself. Now, when we read this, this is n times the square root of 3. So to get rid of a multiply by a square root of 3, I'm going to divide both sides by the square root of 3. Right? Nothing crazy. So I get an answer that looks like this. We have a problem. Don't ask me why. I'm okay with this answer, but mathematicians are not. They don't like a radical in the bottom. And part of the reason why is you'll see the pattern that we're working on today. We have to get the denominator to be a positive number or eventually just reduce out. So the only way we can do that, and this is the rationalizing the denominator part right here, is we need to get rid of the square root on the bottom. And to do that, we're going to multiply both the top and the bottom by the square root of 3. Now notice, that doesn't change our answer. This is like multiplying by 1, because we know the square root of 3 over the square root of 3 is really 1. So knowing that, it doesn't change the meaning of our problem. You can always multiply by a creative form of 1. But what this does is look at what happens up top. Up top, we get 18 times the square root of 3. We can't multiply a whole number by a radical, so we just write it as 18 square root of 3. But on the bottom, well, wait a minute, isn't this the square root of 3 times 3, which is 9? And what is the square root of 9? It's 3. And then the whole numbers, 18 divided by 3, actually produces a nice result. So n is actually equal to 6 square roots of 3, and this is what the act of rationalizing the denominator is. It's getting rid of the radical on the bottom. All right, so I'd like you to try that with this second one. I'm going to pause the video that I'm making, but go ahead and try the second one. All right, let's go through this one quick. So my goal is to get rid of the square root of 2. Well, this is n times the square root of 2, so to undo a multiply by the square root of 2, we're going to divide both sides by square root of 2. And what happens is the square root of 2 is reduced out. You're left with n on this side, and then you can save some steps. You don't have to rewrite it like I did. Notice I've got 7 divided by the square root of 2 on the right-hand side. So I have to get rid of that square root of 2 by timesing by a creative form of 1. And what that does up top is that leaves me with 7 times the square root of 2. But on the bottom, 2 times 2 is 4 under the square root, and the square root of 4 is 2. Now notice, this isn't as friendly because 7 is not divisible by 2, and we don't want any decimals here, so we're going to leave it as 7 halves, or 7 square roots of 2 times 2. So we're going to be using this skill throughout today to simplify. And just so you know, when we say rationalize the denominator, it's getting the denominator to not have a square root in it. Okay. Today, we are learning something that is, I've said this before, but this unit is the most important unit of geometry. We're going to use this for every single math class that you're going to learn in high school after this. And this is one of them. We're going to learn special right triangles. It's 7.4. The special right triangles are ones that have degree measures of 45, 45, 90, and 30, 60, 90. And we hinted at those in the warm-up. So there are patterns that will allow us to solve problems faster because they are special right triangles. All right, so you don't have to write the learning target. Just title it Section 7.4, Special Right Triangles. And we're going to walk through this one first. Now, I don't think you need to write this first part. Okay, what I'm going to do up here, you don't need to write because we're going to regenerate it down below. I just want to show you, where does this information come from? So what happens if I take a square and then I cut it diagonally in half? Okay, it doesn't matter which direction, but let's say I cut it in half. Well, what does that create then? That creates I'm going to flip this around so it actually looks like the half that I wanted. If I take this half of a square and just pull it over, what do we have then? Well, in a square, I actually have, oops, sorry, wrong. There we go. In a square, let's call this n. A side length in a square is n, 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 right? All 4 sides are equal, so this is n, this is n. Now, another thing about a square is it's 90 degrees. Right? So if that's 90 degrees, how long is the hypotenuse? Well, we know Pythagorean theorem. C squared has to equal a squared plus b squared. Now notice, we don't know what they are, but I called them n because they're equal. Now here's the other thing. I can also put equal markings, and notice, this is a key part today. If these side lengths are equal, it's an isosceles right triangle, which means the base angles are the same. And notice, this diagonal cut the 90 degrees in half. So if I cut 90 degrees in half, each one of those angles ends up being 45, 45, and then we've got the 90. So this is our special right triangle, and our job is to simplify and find an expression for the length of the hypotenuse. Well, if I have n squared plus n squared, that means I have 2 n squareds, right? Got 1 n squared here, 1 n squared here. When I add them up, I have 2 n squareds. Then I have to take the square root of the whole thing. But as we've learned, the square root and a squared reduce each other out. And what I have here then is I've got the square root of 2 times the square root of n squared. Well, if c squared and the square root reduce out and I'm left with c, the square root and the squared are going to reduce out and I'm left with n. And then it's going to times by the square root of 2. I'm just going to put the square root of 2 at the back part. So now, here is my expression for the length of the hypotenuse. But how do we use that? Well, what did we just have in our warm-up? Didn't we say this length was 10 and this length was 10? So then that automatically meant that the hypotenuse was 10 square roots of 2. Well, what if it's 18? What if this side length was 18 and this side length was 18? That just makes the hypotenuse 18 square roots of 2. So by doing this work right here algebraically and figuring out a formula for the length of the hypotenuse, we don't really have to do much work when we have a 45, 45, 90 triangle, because we'll be able to figure out using the patterns that we have. So here's what I'd like you to write. If, and this is one of our theorems, if we know for sure that it is a 45, 45, 90 triangle, then it's an isosceles right triangle, and the hypotenuse is the square root of 2 times the length of each leg. So I like to think of this as like a formula. And if we know that both sides are equal, then we know the base angles are the same. And we get 45, 45, 90. So I'm going to pause here so you guys can write this down. Okay, so let's look at a couple problems that allow us to use this special pattern as we go about. Oh, you know what? Did I skip one here? No. Okay. Sorry, I thought we had an extra example in there. We're going to do the next pattern, and then we'll do some examples. So it's up to you if you want to write this one. I actually think I would recommend you write this because it helps give us an idea of where the information comes from. So what if I give you an equilateral triangle? Okay, now remember what equilateral means. It means all 3 sides are congruent. If it's equilateral, it's also equiangular. Now, what if I take and I drop what's called an altitude? An altitude is the same thing as the height of a triangle. What if I cut this triangle in half? And now keep in mind, this was equiangular. So this angle is 60. This angle is 60. And then because the altitude is in an equilateral, we haven't really talked a lot about this, but it's also an angle bisector. It splits this up into 30 and 30, which is still 90. So equilateral and equiangular. And then notice the altitude is perpendicular to the other side. So that gives us a 90-degree angle technically on both sides. So what if I cut this in half and I only focus on half of the triangle? Okay. So now I want to find a formula, a pattern for this that relates all the sides together. And you got to kind of hear me out on this. What if I call each side length of the original equilateral triangle 2n? So if that's 2n, that's 2n. Now notice, I cut this in half, right? So if this is 2n, that means each one of these pieces cut in half is an n and an n. So what I'm going to do is transfer those lengths over here. Half of the side length was n. The full side length of the triangle was 2n. And then our job is to figure out what is the measure of the side length across from the 60 degrees. So I got to figure out, we can call this B or A, it doesn't matter, but we know the hypotenuse. So we're going to do Pythagorean theorem here. I'm going to take the hypotenuse squared, and that has to equal n squared plus, let's call it B squared. Right? So I'm looking for the length B here, and it's just algebra now. I have to be very careful. My calculus students just made this mistake on their last test. When you're squaring, remember, you're squaring each piece inside. Right? So 2n squared, well, 2 squared is 4. N squared is just n squared. And then we can't do anything on the right side to simplify it. But what I can do is move the liked terms over to the other side. So I'm going to subtract an n squared over here. Now remember, this is 1n squared, so I have 4n squareds, and I'm taking away one of them. So I have 3n squareds left over. And then my goal is to get the length of b by itself. So I'm going to take the square root of both sides. And when I do that, remember the square root of 3 and the square root of n squared can be separated under their own radical. And oops, the b squared, the square root and the square root go away, so I'm just left with b on the right-hand side. Right, so now, what's left over? The square root and the n squared, those go away, so I'm left with n, and then we always write the radical at the end. That square root of 3 is just going to be at the end. So, the missing side length now is n square root of 3. That is the missing side that we needed. Now there's kind of three levels of problems here and that you're gonna experience. The easiest one is, what if you don't have to write what I'm doing in green here, but what if we think about that warm up we just had? What if I tell you the shortest side, the one across from the 30, was 12? All right, so if that side is 12, well then the hypotenuse is 2 times 12, which was 24. And then the side length across from the 60, which this will always be across from the 60, is just 12 times the square root of 3. And notice that's the warm-up we just did. But now we're saying you can find these answers if you only know one side of a 30, 60, 90. You don't need to know both to do the Pythagorean theorem. So here is the official theorem. Now it's up to you if you want to write the words. I don't think you really need to. It's the picture that does the most justice. Now notice our picture is flipped around, and that's what's going to be true is you can flip and rotate these pictures as much as you need to. So the thing we have to know is that the smallest side is n, and that will always be opposite of the 30-degree angle. And then the 2n is always across from the 90, and the n squared of 3 is always across from the 60. So this picture is the same thing as we just wrote right up here. But this is kind of our formulas for the 30, 60, 90 triangle. I'll give you some time to write that down. Okay, so we just learned the 45, 45, 90 and the 30, 60, 90 right triangles. Let's apply them now. And we're going to do these together to start. But our goal is to find the missing sides for each triangle. And I will say that there's some problems that are easier than others, and there's some that require a lot more algebra work. So be careful. All right, go ahead and draw the first picture here. And one of the things that I like to do before I start trying to solve a problem is I want to think about, what do we know, right? What does this triangle tell me? And it tells me that I have one 45-degree angle and a 90-degree angle, which means that if I did the triangle sum theorem, we automatically know that this angle has to be 45, because 45 plus 45 is 90, plus another 90 is 180, which proves right here that I have a 45, 45, 90. Now, I always do this. Base angles are the same, which means the side lengths are the same. And that kind of helps me with my formula. So I'm going to grab my red pen, and I'm going to put the formulas around the triangle from our special right triangle. So what was it? Across from the 45 was n. Across from the other 45 has to be the same value. So n, and the hypotenuse was always equal to n square root of 2. All right, now, all we did was place the formula. When you do that, you will then have one problem that you can solve for n. And notice this is just like the radical work that we did at the beginning of class. So my goal is to solve for n. I'm going to do this down here just because if anybody's looking back at these notes, they'll know where it came from. So my goal is to get n by itself. Well, this is n times the square root of 2. So I'm just going to divide both sides by the square root of 2. And that reduces the square root of 2 out on the right-hand side. And then I'm left with 8 square root of 2, 8 divided by the square root of 2. But we do not like having this denominator as a radical, so we have to rationalize the denominator. Which means we're just timesing by both the top and the bottom by the square root of 2. And again, you can, if you understand what's going on, you could skip a couple steps here, but the top part is 8 square roots of 2. The bottom, wait a minute, 2 times 2 is the square root of 4, and the square root of 4 just turns into 2. So this is the part I kind of do in my head. But then I've got 8 divided by 2, which is just 4. Notice how I'm not dividing the square root of 2, because it's just dividing the whole numbers out. 8 over 2 is 4, and then it's times by the square root of 2. So what did we do? We just found n. Well, what was n? N was the lengths of the other two sides. So now I know that this side length is 4 square root of 2, and this side length is 4 square root of 2. And we automatically knew the hypotenuse was 8. So now I know all 3 sides, and I know all 3 angles of this triangle. And I think it's important for you to understand. Notice how we didn't do Pythagorean theorem. We couldn't, because I didn't know the other side length. So right now, the only way we know how to solve this problem is to use the special right triangle formulas. I will say next Friday, you're going to learn another method that you could use for solving this, but right now, this is all we know. All right, the next problem. Let's take a look at this one. Notice here that it only has one side length. It's a right triangle with one side length, so I can't do Pythagorean theorem. To do Pythagorean theorem, I need a second side length. So Pythagorean theorem will not work, which means we have to go to our handy dandy bag of tricks, and I know that I have 30 degrees and 90 degrees, which means this angle here has to be 60 degrees, right? Because 30 and 60 is 90, 90 plus 90 is 180. So now I know it's a 30, 60, a 30, 60, 90 triangle. Grab your formula marker or your formula pen, whatever. I always use a red pen, and I go across from the 30 first. Notice 30 degrees is the smallest angle, and across from that side is always 1 n. But I usually don't write the 1, I just put n. Right? And then across from the 90 is the largest side, 2 times n. And then always across from the 60 is the formula n square root of 3. Now notice, n is the smallest, doubling n is the largest, and timesing by the square root of 3. The square root of 3 is less than the number 2, which is why this is in between these two sides. It's a middle size length, which is the 60 degrees. So that's kind of how I memorize this formula. Well, now look at what happens. We actually don't have to do the same work we did in number 1 because 7 square root of 2 is equal to n. This problem was actually pretty friendly in the fact that they're telling me what n is. So all I'm going to do is go to the formulas, and I'm going to plug in 7 square root of 2 wherever I see n. So notice if I take 2 times n and I plug in the 7 square roots of 2, remember when we're multiplying, we're only multiplying the whole numbers together. So 2 times 7 is 14, and then you just leave the square root of 2. So there's my hypotenuse. I might try to pull this down if I can, so I have a little more work up top. All right, now I have to take 7 square roots of 2 and plug it in here. So I'm going to do this up top, 7 square roots of 2. That's my n. And then I'm going to times that by the square root of 3. Well, we did a problem like this the other day when I'm multiplying radicals. The 7 stays, and then I get the square root of 2 times 3, which is 6. And I do want to think about, could I break down 6 into some factors? But none of the perfect squares go in there, so this is completely reduced. And that means that the side length that's across from the 60 is 7 square roots of 6. Now look at our answers. They're not friendly, right? But they're reduced, and there are no decimals. All right, let's try another one. All right, so notice, as you're drawing this picture, hopefully you're already identifying, all right, we have a 90 degree, we have a 60 degree, which means this remaining angle has to be 30. All right, now I want you to take your red marker and I want you to put the formulas around the 30, 60, 90 triangle, just like we did in this one. See if you can put them in the right spot, because that's the start of this whole process. Okay, so hopefully you said across from the 30 is the smallest side length. That's our n. Across from the 90 is the largest side length, which is 2 times n. And then across from the 60 is the middle side length, which is n square roots of 3. So notice, by placing those formulas, one of them gives me an algebra problem. I have to solve for n. So I don't have a lot of work. I'm going to just do it down here. I've got 15 equals n times the square root of 3. So what do? We have to undo the multiply by the square root of 3, which is just division. And then you'll notice the square roots of 3 reduce out. So you're left with n. But then I've got 15 divided by the square root of 3. And this is where I like to rationalize the denominator right here, kind of in that same step. So up top, I will have 15 times the square root of 3. That's in my numerator. The denominator, well, the square root of 3 times the square root of 3 is the square root of 9. But wait a minute, isn't the square root of 9 just regular 3? And then look at your whole numbers. You got 15 divided by 3. Well, 15 divided by 3 is 5, and the square roots of 3 just stays as is. So what did we just find? We found n. So I'm going to go back to my formula and find the missing sides. Well, this one's really quick. N is 5 square roots of 3. So here's this side length. We already know 15. And then all we have to do is double the 5 square roots of 3. And you could do this in your head if you want. You technically don't have to show this step right here. But 2 times 5 is 10, and then you just leave the radical as is, because you only multiply whole number by whole number. And now I know all 3 of the side lengths, as well as all 3 angles. All right, so we're at our last problem here. If you're watching the video online, go ahead and hit pause, write this one down, and see if you can try it. But what we're going to do is we're going to go over this really quick, and there's one tricky thing that you have to be aware of before we can start. And you're always allowed to do this. It doesn't come up often, but I think it's important for us to notice something. So look at the length AE. All right, we know that length is 12. Which means we know a couple other pieces as well. If that length is 12, and the congruent markings state that this length is 12 as well, then. And notice how that this basically, angle A and angle E are 90 degrees. These are consecutive interior angles, which means these two lines are parallel, which is kind of key for what I'm going to do next. Now, here's the trick in a problem like this that you can always do. You can draw in an extra line when you need it. What if I take AE, which we know is 12, and I just slide it all the way over until it hits D? Well, what that did right there is we drew that line in there, but that gave me a couple more pieces of information. I pulled this over so it was parallel. Because I drew it, I can conclude that this has to be 90 degrees, as well as this, because these are a linear pair. Well, then wait a minute. What does that make this in here? That makes this a square. So I not only know that we have 90 degrees, but I also know that these side lengths are the same. So A to this new point is 12. The distance from that new point to D is also 12. Okay. Now, that almost gives me what I need for my triangle right here. I know it's a right triangle. I have no way right now of figuring out this angle right here. I don't know it yet, but that's I do need to know it. But what about the other angle? What about this angle right here? Doesn't that form a linear pair? We haven't used this one in a long time. Linear pairs, they're supplementary. So if this is 150 and it makes up a straight line, the only possible angle measure for this one is 30 degrees. Well, wait a minute. If this triangle has a 90 and a 30, now I know what this angle right here is. It's 60. So I had to do a little bit of creative work and use linear pairs to figure out that I actually have a 30, 60, 90 triangle hidden within this picture. Now notice, across from the 30, I'm going to take my red pen and we're going to put our formulas. Across from the 30 is the smallest side, that's n. So n is equal to 12. Across from the 90 is the longest side at 2 times n. And always across from the 60 is n times the square root of 3. So there are the formulas. That's our new special right triangle. And look at how friendly this problem actually became. I know that the side length n is 12, which means this side length db is 2 times 12, or 24. So there's my first answer that I found. And then the side length across from the 60 is 12 times the square root of 3. And we just write 12 square roots of 3. So what does that mean about the side length AB? Well, AB is the full length of 12 plus the 12 square roots of 3. And we have to be very careful here. We talked about this the other day, but it hasn't come up a lot. What are those two answers? AB is 12 plus 12 square roots of 3. You cannot add these together because they don't have like radicals, which means you are done. That is as far as you can go without using a calculator and finding decimals. And sometimes our answers look like that, and that's okay. It's mathematically accurate. I just want to point this out. So I thought I had a slide on here. Wednesday, the 11th. Your instructions for that is to log into Schoology and take the quiz. The quiz is 8 questions. There are, I believe there's 6 multiple choice questions. There's 1 matching, and then there's one where you just type in the number after you do the work. But what are the sections that we're covering? 7.1, 7.2, and then today is 7.4. So what are those topics? Topics are Pythagorean theorem, which is just c squared equals a squared plus b squared. 7.2 was the converse of the Pythagorean theorem. Which this is the part I want to make sure you guys are aware of. So if you understand that c squared equals a squared plus b squared, then we know we for sure have a right triangle. Right? But what if c squared is larger? If the hypotenuse is larger than the other two sides, then we have an obtuse triangle. And what if the a squared plus b squared ends up being, or larger than c squared? So what if c squared is smaller than the other two sides squared? Then we have the acute triangle. So that was what 7.2 was all about. These relationships, in the way I think of it, greater than means obtuse, but that's only true if you put c squared on the left-hand side. All right? And then what we learned here is your 45, 45, 90, and your 30, 60, 90 triangles. So that's the quiz. Please make sure you have done these homework, and then that's what we're doing tomorrow. Okay, homework tonight. I can come back to the slide if you need to, but let me just show you this. Homework tonight is 7.4. It's in your textbook, and we're doing 1 through 10, 13 through 17, 23, 24, 27, 31. So that's all I have. If you have questions, you can stick around. If you don't have any questions, you are free to leave and work on the homework tonight.